Hey everyone, in this video we're going to continue with working with more line integrals, and today we are going to talk about the fundamental theorem of line integrals, aka why we love conservative vector fields so much. So let's go ahead and get started. We'll begin by just kind of reaching back to Calc 1, where we talked about the fundamental theorem of calculus, which told us that if we are integrating from a to b of the derivative of some function with respect to x dx, then this is equal to the original function evaluated at b minus the original function evaluated at a. I mean, like we've been using this all along. Every time you take an integral and you evaluate it, this is exactly the idea that we're applying. And it's really nice and quite convenient to be able to say this to get a specific number at the end. And one of the great things about working with conservative vector fields is that it allows us to come up with something that is equivalent to this, kind of in higher dimensions. So the line integral equivalence takes this idea of the derivative in the higher dimensions and tells us that the integral over a curve of the gradient of a function dotted with dr is equal to that original function evaluated at the end point of our curve minus the start point of the curve, or f evaluated at the start point of the curve. Okay, so you can actually skip all of the parameterizing, or well, sometimes you can skip parameterizing your line, sometimes you can't, but you can skip all of that stuff that we did in our last video by simply saying, okay, if I can figure out what the start and end points are for the curve that I'm looking at, and I know that I have a gradient inside of my integral, then I just have to reconstruct my function f, plug in those points, and do the evaluation. Same way that we would with Calc 1 here. So more formally speaking, the fundamental theorem of line integrals which will from here out be called FTLI, because I am not writing that out over and over again throughout the rest of this video. This tells us that if F is a conservative vector field, which has a potential function little f. So what this means then, if we have a conservative vector field, it's got a potential function. The definition of this is that the gradient of little f is equal to our vector field. Then we have that the integral of some curve in our vector field dotted with dr has to be equal to little f at the endpoint minus little f at the start point. And that's for our curve C. Okay. Okay, so I mean, like, how do we use this? What does this wind up looking like? To apply this, what we do is one, we compute little f by recovering it from the fact that our vector field is equal to the gradient of little f. And then two, we plug in start and endpoints for the curve C. And I want to point out that we may need to determine what these are exactly with some parameterization. But one nice thing about this is that, okay, yeah, maybe you still have to do the parameterization, and yeah, you have to recover your potential function, but it saves you from possibly having to do a really kind of nasty integral after you take that dot product that pops up with our typical equation for being able to work with the line integral in a vector field. So let's go ahead and work some examples and practice applying this really nifty theorem. So in all of our examples, it'll be the same idea as last time. We will integrate the following, except I guess the difference is now we know that they're conservative. We're going to start by being told that they are conservative vector fields on the given curve. Okay. So this time we do know that they are conservative. In my last video, we talked about working with non-conservative vector fields, and you can actually apply that idea to that whole big process. You can apply them to conservative vector fields as well, but there's no point in going to that much work because, well, it's a conservative vector field, and we have this nice theorem that goes with it. So. First example, we are going to take our vector field to be equal to yx, and our line segment, our curve will be a line segment from 0, 0 to 1, 1. Okay. So to be able to figure out this integral, we already know it's conservative. Typically, you would want to check though, okay? And you check that using the test that we learned in a previous video, working with either the curl or checking to make sure that those partial derivatives match up the way that you want them to. But since we're already given that it's a conservative vector field, we're not going to mess with checking, and we're just going to go immediately to applying the fundamental theorem for line integrals. And that tells us that the integral over C of f dot dr can be written as f at the end minus f at the start, where f is our potential function. So step 1, recover f. And so we're looking at this right here, and to recover f from its gradients, we note that f has to be equal to the integral over the partial derivative with respect to x of f, so it's going to be y dx, and that's just equal to xy, and then it's plus some unknown function in terms of y, and then f also has to be equal to the integral over, now it's the y partial derivative, so x and then dy, which is also just equal to xy plus some unknown function in terms of x. So these two agree, the xy, and neither of them contribute any new information. So there's not really anything new that we need to worry about with those unknown functions. So our potential function f xy has to be equal to x times y. Okay. So, and I do want to point out, a lot of times in previous videos that we've talked about, okay, there's some unknown constant that we've had to add on. Well, in this case, we don't care about the unknown constant. And that's just simply because it's going to cancel out when we do the subtraction here anyway. So it winds up just going away. So we're really not too terribly worried about what that is. Okay, so this is our potential function. And now we just need to evaluate it at the start point and end point. So our starting point, if we go back to the statement of the problem, we're told that we're starting at 0, 0. And our endpoint is 1, 1. So applying our fundamental theorem of calculus here, or fundamental theorem of line integrals, our integral that we're looking for has to be equal to our potential function little f evaluated at 1, 1 minus our potential function evaluated at 0, 0, which is just equal to, we had said x times y, so that's just 1 times 1 minus 0 times 0. So we're just going to get 1 out of that. So yeah, that's pretty much all there is to doing integration when you have a conservative vector field. It makes everything so much simpler. And it's actually about to get, it gets even better. So I'll show you our next example and then we'll kind of connect the two. So in this example here, we have, we're going to use the same vector field, yx, and we're going to line segments from 0, 0 to 3, negative 4, followed by the line segment from 3, negative 4 to 1, 1. Okay, so again, since we know that f is conservative, because we were given at the very beginning of this that f is conservative, we apply the fundamental theorem of line integrals. So the integral of over the curve of f dot dr, which is what we want to compute, is equal to the potential function evaluated at the end minus the potential function evaluated at the beginning, where we find our potential function knowing that the gradient of it is equal to our vector field. Okay. So step 1, recover little f from the vector field, which is equal to its gradient. And in this case, f was equal to the same vector field that we had earlier, so we already did this. And we said that our potential function was x times y. And now our step 2 is to evaluate at the endpoints. So we had said that we started at 0, 0. And we end at, okay, so we have 0, 0, and then we go to 3, negative 4, and then we go from 3, negative 4 to 1, 1. We don't care about this 3, negative 4 at all, because the main point of this is that the curve started at 0, 0, and it ended at 1, 1. So we actually can skip that whole middle step right there, and we just say we end at 1, 1. So we have the integral of c f dot dr equal to our potential function evaluated at 1, 1 minus our potential function evaluated at 0, 0. Well, we've already done that. That was just equal to 1. Notice that that is exactly the same as the answer that we got last time. Okay. This is because the value of our integral when we're working on a conservative vector field is really only dependent on where you start at and where you end at. It doesn't really care what you did in the middle. And I would like to encourage you, if you have a little bit of time, to go back and look at that last video I did on just generally speaking, integrating over vector fields, and compare with the first 2 examples. In the very first 2 examples of that, I have a curve. It starts and ends at the same points, but the paths between the 2 are different. And we get different results. The reason for that is because the vector field in that case is not conservative. But as soon as we have a conservative vector field, the only thing we care about in trying to evaluate it is where it starts and where it ends. because the potential function for that vector field is going to be the same regardless of what curve I have. And so I just need to look at start and end points. And that is one thing that is really extra special about conservative vector fields, is that it makes the work so much easier, because we basically already did this problem. But if we had gone through and like parameterized it, we would have needed the two parameterizations and it would have been a lot messier. But because it's a conservative vector field, we can just say, I can pick any path I want between the 2 points. So this is so important. I'm going to write it down and put it in a box. So when integrating a conservative vector field, only the start and endpoints of the curve matter. Box. We do not care what that curve looks like between the start and the endpoints, only what the start and the endpoints actually are. And let's actually explore that a little bit farther with an example that's got even more moving pieces to it. So in this example here, I'm going to have my vector field be equal to e to the x sine of pi over 4 times y, and then pi over 4 e to the x cosine of pi over 4 times y. And my curve is going to be equal to the line segment from 6, 0 to 0, 6. Okay. And once again, we were already told way back at the beginning of all of this that f is conservative. So what this means is that the integral over our curve of f dot dr is equal to f evaluated at the endpoint, where little f is the potential function, minus little f evaluated at the start point. So our gradient of little f has to be equal to our vector field, okay? Because that's what it means for the vector field to be conservative, right? So step 1, recover f. Well, sometimes you can get away with doing this by inspection, and we can kind of look at it a little bit and be like, okay, the only part of this that had an x in it was that e to the x. Well, this piece isn't changing, and well, the y part didn't really change. And so we kind of know that maybe our answer should be e to the x times sine of pi over 4y. But we can go ahead and go through the motions with this anyway. F of xy is equal to the integral e to the x sine of pi over 4y dx. Well, that's just equal to e to the x sine of pi over 4y plus some unknown function in terms of y. To find out about that piece there, we do the same idea, but with our y components. We do dy. Applying a little bit of u sub right there, we're going to get e to the x sine of pi over 4y plus some unknown function in terms of x now. Well, these two agree, and neither one of them really adds any new information. So f of xy is really just equal to that e to the x sine of pi over 4y. And then again, we don't really care about the unknown constant. Okay, so this is our potential function, and that's what we're going to use to do our evaluation here. So for this one, we already know that our starting point, we're given that it is 6 to 0, and our endpoint is 0 to 6. So applying our fundamental theorem of line integrals, integral over f dot dr of f dot dr is equal to little f evaluated at 6, 0 minus, oh, nope, I got that backwards. F evaluated at the end, that's 0, 6, and then f evaluated at 6, 0. And we had said that f was equal to, I'll write this over here, e to the x sine of pi over 4 times y. And so I'm going to get e to the 0 sine of pi over 4 times 6, and then minus e to the 6th sine of pi over 4 times 0. All right, so this right here is just going to give me -1 because that part is 1, and then sine of pi over 4 is just sine of 3 pi over 2. That's -1. And then minus, that winds up being 0. Because e to the 6th, I have no clue what that number is, but I do know that sine evaluated at 0 is 0. So that's really the only part that matters. So we're going to get -1 for this integral right here. So that's going to be our final answer in that case right there. Now, I want to compare this to a similar problem on the same vector field, but with a different curve going through it. We have our vector field being exactly the same as before, e to the x sine of pi over 4 y, and then pi over 4 e to the x cosine of pi over 4 y. And in this case, our curve is going to be equal to the piece of the circle x squared plus y squared equal to 36 in the first quadrant. And this time we'll do, it'll have a counterclockwise orientation. Okay. So again, we already know it's conservative. We've already worked with this this function up here. So we can apply our fundamental theorem of line integrals, f dot dr equal to its potential function evaluated at the end minus the potential function evaluated at the start of the curve. But let's kind of take a look at what this curve actually looks like, okay? Like what would our end and our start points actually be, okay? So our curve here, this is going to be the circle with radius 6. And we just want x to be greater than or equal to 0 and y to be greater than or equal to 0 because we're looking at our first quadrant. So it's going to be something kind of like that. And we're going in the counterclockwise orientation, like so, which means that our start is down here and our end is up here. And I'm still working with like x and y coordinates because I haven't parameterized anything yet. I'm just trying to figure out what this shape looks like, okay? And we kind of remember back to the problem we just did. Same vector field. And this time we have a line segment that starts at 6, 0 and ends at 0, 6. Okay? Which means that our start point here and our end point here are the same as our previous problem. So since we have the same start point and same end point and the same vector field, so I should specify that, same vector field, well, then the integral is going to be the same. And this is because we only care when we're working with conservative vector fields, we only care about where they start and where they stop. I don't care if I'm doing a curve like this, or if, like in the previous problem, I have a line segment that looks more like this. This was what we worked with last time. Either way, we get the same answer because we have a conservative vector field. Well, we just saved a ton of work by noting that, because now we know that the integral from C over C of f dot dr has to just be equal to it was -1 last time. That's all there is to it. Otherwise, without noticing that, without having this ability to apply the fundamental theorem for line integrals, we would have to go through and, even like, we could do this all over again, recover that all over again, do the whole parameterizing it, figuring out your start and your end point, all that stuff. Or we can say, no, I have a simpler line that I can use. And we did that in the previous example. And so I can just say, okay, by the fundamental theorem for line integrals that says we only care about start and end points and not about what happens in between, I know that those two integrals have to be the same. And that's it. You've saved yourself a ton of work. And something that's really, really common in homework problems, you always want to check for this, is that, they'll, to prove a point, they'll put both versions of the problem. They'll be like, okay, here's one with a complicated line in it. Here's one with a not so complicated line in it. And they'll have the same start and end point, same vector field, okay? You should do the one that has the simpler start and end point. If you already know the simpler start and end point, you can do that one using the fundamental theorem for line integrals, and then just say, okay, if I have the same start and end point in this problem and the more complicated problem, then I'm going to get the more complicated, or the same answer. And so you just saved yourself a ton of work. So I guess I'll write that down. When you have a conservative vector field, save yourself work by doing problems where start endpoints are easy to determine. And then apply this answer to other problems with same vector field and curves with same start and end point. Because otherwise you would have to go through and just go to a lot more work to be able to figure out, okay, got to kind of like parameterize my curve to figure out the start and the end point, but maybe sometimes it winds up being easier to just kind of look at it, figure out, okay, where does it start, where does it stop, and you can just work with the easier one first, and then your problem's already solved for you. So that's why a lot of times you'll get like a little hint that says, do this set, the entire set, in an intelligent way. Sometimes it makes a little bit sense to kind of look ahead and see which ones are easiest to work with first, and then save yourself a ton of work by doing those easy ones and saying, well, this one must have the same answer. So, but again, that's only for conservative vector fields. If you do not have a conservative vector field, you have to use the other method. So, that's pretty much it. Thank you so much for listening. In a video that I'll be posting sometime in the next few days, I'll go over a couple more just like assorted examples, sifting through whether or not a vector field is or is not conservative, and then applying each method depending on what we need. So see you guys next time.